Hello again,
Yes.
everybody. So we have Venkat today speaking on stable probability distributions. Venkat, please go ahead.
Yeah. Hi. Thank you for letting me speak about this stable probability distributions. I'll begin with the motivation of why we are going through these distributions. So in 2020, I was interested in some simulations of this kind of stable distributions. And uh, I'll begin with the Brownian distribution. So this is a simulation with Brownian distribution where there is a, if you can observe, there's a uniform spread kind of thing happening. This is a kind of visualized as an autonomous carrier who has a circle of his visibility. He has just a circle of visibility beyond which he cannot see what is happening. And how he is controlled is through the random walk or Gaussian walk or a Brownian walk. And wherever he passes through, the blue dots turn to red. And this is the Brownian walk. And similarly, we have something called a Levy distribution. And this here he follows the Levy kind of distribution, where he takes multiple short steps and suddenly he takes a long step. And this is what happens where the spread is not so uniform, and he takes it's very undefined. And and so in the background, what is these blue dots is, we can imagine these as some kind of random distributions of whatever populations or people or whatever it is. And this autonomous carrier is kind of infected with let's suppose a virus or something. And so we are these simulations, studying these kind of simulations for the base goals of whatever from the stable distributions I was interested in. And why are these stable distributions so relevant is what will be going through. And so initially, these kind of distribution, Levy distribution, was first observed by Paul Levy, mathematician, where he observed the foraging pattern of birds, like how birds can gather their food. And that I'll show you the evidence later. But this is the Levy kind of distribution, which has multiple short steps, and suddenly there'll be a long step, and again there'll be multiple short steps. And this is the random Brownian walk, whatever it is, from the Gaussian distribution we can see, which I will show you again later. And it will be more uniform and kind of like this, evenly spread. And so yeah, this image is from this paper that by Andy Reynolds, and it's a recent work which seems to have more information about Levy walks and importance of them in biological aspects, which perhaps you're interested in. But yeah, so Levy flights, that whatever Paul Levy first observed was in bird foraging pattern. This is a recent paper, but this was even observed long back. And this randomly looking distribution, randomly looking paths are taken by different birds gathering for food. The birds are tagged, and they are observed how they gather food. And this is the path they take over a long period. It's not a short period. And these are different birds which are tagged and let alone. And they observe how these distances are how these distances are varying according to a probability distribution. And that will actually give you a Levy distribution, which I'll show you. And again, understanding human mobility. So more importantly, we are interested in human mobility, how humans travel. And again, so in this work, people observed like 100,000 people, mobile phone users. Yeah, how mobile phone users. So they observed the pattern of how mobile phone users were traveling around. Like this is a large data set, like about 6 million anonymized mobile phone users. It was observed, and like the different displacements they took were observed, which is around 16 million displacements were observed. And that again, a probability distribution was observed, and this seemed to follow a kind of a Levy distribution again. And much more again, similarly, dollar bills. The dollar bills were around $500,000 bills were serial, according to the serial numbers, they were tagged and they were studied. How the spread of a dollar bills was studied, and these are all very relevant papers related to the, supporting the claim that human mobility is based on this kind of Levy distribution. And yeah, so now, so this is on one side Levy distribution kind of, which is a stable probability distribution, which we'll try to see what is a stable probability distribution. And on another side, we have this kind of well-known Gaussian distribution, which is again a stable probability distribution. For instance, it's called a Galton board. For reasons, Galton started studying this. So you let individual balls travel along this kind of paths, and they have a probability of 1/2 going from here or here, 1/2 again here, and you can see that it's completely random kind of distribution. And if you let go one ball, we probably cannot say what will be the path of the ball. And again, two balls, it will be completely random. We cannot predict where this falls. But if you, again, n tending to infinity, we take many balls falling in this kind of randomly manner, we can observe that it's a nicely regression towards the mean. All these balls have a tendency to fall towards the mean. And not just that, the fluctuation, the statistical second variance, whatever fluctuation, whatever we know as variance, is nicely follows with the Gaussian kind of distribution.
Yeah.
Yeah.
This
is this is called as a Galton board, and this is a large scale Galton board with many large balls.
I think Venkat John has a question.
Yeah.
Oh yeah, when he gets done explaining. So
yes,
I
sure.
just want to clarify what you meant by stable distribution. And I mean, if this is really like this is like a special property. I know, like Gaussian,
I have not reached the point of I have not reached the point of what is a stable problem. I'm just kind of motivating what are the different distributions. One was the Levy distribution, which I think I have not shown, but I've shown you how the Levy walks happen. These are the kind of the Levy, how the Levy walks happen, and this is how the Brownian walks happen. And these are very related to the distributions. How the walk happens is dependent on the distribution. And so this is again the Galton board, a much more smaller scale version, which again beautifully shows the Gaussian distribution happening. So this is the Galton board. And so I have to go to the stable distribution part, but before that, I'll still motivate a little bit on the.
Oh no, you could go as you plan. Thanks.
First, I wanted with the mathematics, but images seemed a much more attractive way to attract. And so this was first studied by Galton, Sir Francis Galton, in his work regression towards the mean. And he has these ideas about nature versus nurture and everything. But these are some beautiful concepts I won't be exploring. But so this problem happened initially. I was interested, what will be if you take for instance, our college, what will be the probability, not the probability, percentage of physically disabled people that you can find in this college itself. And it seems like around it will be around 2 to 3%, because persons with disabilities actually have this kind of 3% reservation that they can be allotted in a college and everything. And this seems to nicely actually match with the actual data with what is the distribution of people physically disabled. If you take population distribution. And this 2-3% is actually nicely also falls with the whatever 3 sigma deviation from the normal distribution. I have to tell you what are the sigmas and mu's, which I'll tell you now. But yeah, which seems to be a remarkable concept. Like if you take like the physical abilities of human any beings and you scale it like this, I mean you take it around this scale, and if you try to see the probability density of them, it may, again this is all this all whatever we are seeing is for n very very large number, but it may follow this kind of a normal distribution where the people with disabilities will be like around 2 to 3%, and people with super abilities maybe with 2 to 3%, and most of them will have this mean kind of physical abilities. And this is the whole motivation of the central limit theorem, where that different independent identical distributions will, when you sum them up and reorder them, they will have this kind of a Gaussian distribution. What we saw in the Galton board was kind of like that. Like each and every ball is an independent, you can imagine like an independent distribution, and it is identical to each and every other ball. And all these balls all together, when you sum them up, it follows kind of a Gaussian distribution, which you can see in this, which you can see the derivation in this Feynman lectures, a very basic derivation, not the regular derivation. But
is each individual ball, does that have a Gaussian distribution itself, or just the sum of them?
Yeah, like yeah. If you, how would I see the Gaussian distribution from each and individual ball? You let it run individually 1,000 times or 10,000 times.
Yeah.
So
Okay.
it's a Gaussian distribution. Yeah.
Okay.
And you let, and the identical ball, it's again an independent distribution. I'm imagining it like that. And so yeah, I'm saying, and you sum all these distributions, follow, they will have this mean behavior and a statistical fluctuation of this kind of variance. Now I have to explain to you what are these mean, variance, and all these, which I'll be defining it then. So far, hopefully.
Oh, did we lose him again? No, Venkat is still there.
Connection.
Maybe switching, because he was switching over or something.
Possible. Yes.
Sorry.
Yeah.
I keep going off.
Yeah.
Yeah. So was I clear so far? I mean,
Yes.
We lost your audio.
any?
I think.
Yeah. Okay.
Yeah. Go ahead.
So if, yeah. Okay. I was just asking if there are any queries so far with whatever I've discussed so far. I just showed you the different instances where you can perhaps see Levy distributions and Gaussian distributions. And now
I have a question. You use the word fluctuations.
What is required?
I have a question, Venkat.
Yeah. Not. Yes.
You use the word fluctuations in describing the variance. I think with that, what do you mean by fluctuations?
Yeah, I should not use perhaps the word fluctuation. I just mean the statistical fluctuation around the mean. The probability distribution, whatever is there, it has this nice feature that around the mean, it has a fluctuation. Yeah, maybe I should not use the word fluctuation.
No, I was just curious. Fine.
That is the variance. And so I was was just saying stuff. Fluctuation.
Yes.
Yeah, maybe I should not use the word fluctuation. Yeah. Deviation from the mean. Deviation from the mean is. Now I have to describe to you what is happening, what is the probability distribution, and what is everything. And so yeah, I'll take any random variable and carry of x such that probability of a number of outcome is less than s, less than x. And by my definition, you can see that if I take the limit x tends to infinity, capital P of x should be 1. Like I cover the entire region, and limit x tends to minus infinity, capital P of x will be 0. And so the capital P of x will have a feature such as this, where this is 1, P of x is equal to 1. And yeah, now I defined the actual, this is called the cumulative probability distribution. And now actually different, what is a probability distribution function? Small p of x such as d dx. And if I take the same kind of scale, this will have features such as this. And again, this is when x tends to infinity kind of behavior, and this is x tends to infinity kind of behavior. And you can observe that this small p of by my definition. And based on this small p of x, I can define an expectation value e of x such as expectation value of e of x such as e of x small p of x dx. This is the expectation of e of x. And now I should define the defining features of this kind of probability distributions, which are moments. And
is there a limit on that integral? Are there limits on that integral?
The same limit as.
But then the left-hand side should not have x, right?
Yeah.
The left-hand side then should not have x.
Why?
Because it is integrated off.
I didn't understand. So, like
because it is
like,
integrated
what
out.
is happening? This is from minus infinity. P of x can be defined from minus infinity to plus infinity, right?
Okay.
Integrated out.
I was saying the expectation.
No, e of x, I'm defining it. Value of x.
But if you put the finite limits, then x is a integration variable, right? It cannot appear on the left side. Like unless it is an indefinite kind of, I don't know even, yeah, integral.
Maybe this is like the Fourier transform variable.
So there should be some other variable then, right?
No, this is, I'm saying this is the expectation value of this will not define how cans and not define. Okay, okay, now yeah. Expectation value E, I will call it E, and yeah, I get what you meant. So yeah. And okay, I'll define the moment, which is x power And this is the main characteristics of any probability distribution, which we'll come to see about. So based on this mth moment, I can characteristic function. Yeah, I see now what you meant. E power minus I x is yeah. So this thing p of k, which will be like as ikx small p of x dx. Yeah, this is like the Fourier whatever we were trying to say. Yeah, it kind of makes sense now. Anyhow, so this is a characteristic function, and it's also a moment generating function. This is a moment generating function because of I can write it as and this will generate the moment. This is p of k. Yeah. So based on this, now we call the cumulant generating function. It will give me cumulants, which will define as some as lambda. Okay. And this subscript C, which denoting that is a cumulant. And so the relation within this cumulants will give me the importance of the elements which are responsible for the probability distribution. For instance, the first cumulant will give me the mean, and the second cumulant will give me the standard deviation or the variance, and the third cumulant will give me the I won't write the expression for this skewness moment. Fourth cumulant will give me the kurtosis, and these are the defining character of any if you see a probability distribution function. For instance, the how the spread of this distribution will happen, which will be sigma, or and this will be the mu, how we define it. And skewness, what will be skewness is whether the distribution function is skewed towards left or towards the right. This will give you the characteristic of the skewness, and how this distribution function is dying off. This will be the measure of kurtosis, tailoredness, and you can keep on going for higher cumulants, which will just be the hierarchy of like whatever description is needed to go for higher, better and better description of a probability distribution function, essentially. So now we have hopefully all the tools to describe the probability distribution functions, and I'll get back to my
Paused our video so that maybe
Sorry?
it will help. We have paused our videos. Maybe it will help your bandwidth because your voice is breaking up.
Okay.
Yeah.
Oh, sorry. Okay.
But that's okay. Like, I mean, so just that, I think it might help you now. it is
Yeah,
better.
okay.
Can I ask a question?
Sure. So far, any doubts? Yeah. I should probably
So
stop here. Yeah.
it seems like for skewness, you're just shifting the mean. No?
Shifting the mean. It doesn't just mean the mean shifts, but also that the entire distribution is kind of tilted. If you see the black
it's
body
tilted.
radiation, yeah,
Okay, I see. Sorry.
I'm not really good. Yeah,
Okay.
the
Oh, I
mean
see,
can
I
be
see.
the
Never
same.
mind.
The mean
Yeah,
can be the same, but the entire
I see.
distribution can be tilted.
Okay.
Yeah, the perfect example is the black body. It's not a Gaussian. If you see, yeah, it's not at all Gaussian. I should not compare it to Gaussian, but yeah, it has a tilt towards the black body radiation. If you observe it, and that has a kind of a skewness to it associated to it.
So is
Yeah.
the skewness kind of like a measure away from Gaussianity, or?
No. Gaussian, we have only mean and variance.
Yes.
Sigma and
Okay.
mu. I'm giving a description for a general probability distribution function,
Okay.
and that includes all this skewness and kurtosis, and it keeps on. And this hierarchy will tell you what is the importance of, what is important, more and more important in describing a probability distribution function.
Okay.
Yeah. So yeah.
Could you give one example where, like, normally we see like variance most prominently used. Could you give an example where this third cumulant is important? Like, what is like
just now I said the black body radiation, which seems to have a skewness kind of behavior, which is it's skewed. I don't remember exactly how it's skewed, but yeah, the black body radiation is, if you observe, it has a skewness nature of association to it. It is tilted. How it is tilted?
okay.
Yeah, I forgot how.
Some sort of asymmetry.
Also forth, yeah.
Yeah.
Okay.
And yeah, now and kurtosis or whatever it is, the measure of tailoredness, how this distribution will die off, and this seems to play an important role in the Levy distribution and the Gaussian distribution. In the Gaussian distribution, the spread was even, the simulations, whatever I showed, because it dies off nicely. But the Levy distribution, they have this kind of long, they travel really long distances, and that's why, it goes like this, and it's not a peak. It has a long tailoredness nature, which seems to be very important in this kind of Levy kind of distribution. So we'll be seeing where this long tailoredness also is present in other kind of distributions. And yeah, so far, am I making sense? Any more queries?
No, good. Yeah.
Okay.
Go ahead.
Thank you.
Thanks.
Yeah. And yeah, so I talked about Levy distribution and Gaussian distribution. Yeah, and the Gaussian distribution seems to be prevalent in many scenarios, like heights of people. This can be even seen in a classroom, I suppose, but a large classroom. Always say take n, capital N, always large number, the number of people or whatever it is. And yeah, these are many more scenarios which you can see in this Galton board site where there is this Gaussian kind of distribution happening. It's not really nice because if you observe here, there is kind of a deviation. Anyhow, that can be captured with the higher cumulants, hopefully. Yeah. Interesting that salary distribution of people, if you observe in different countries, seems to have this Gaussian distribution. But then came the long-tailed distributions, which was observed by Wilfredo Pareto for the first time. For instance, how wealth is distributed among people, that was the salary, and how wealth is distributed. It seems to have this odd behavior, like 20% of the population owns 80% of the wealth. And this long-tailedness kind of nature is what is the characteristic feature of this Levy distributions or Pareto distributions. And all these distributions are actually also interestingly stable distribution. Yeah, now I have to come to what is a stable distribution. The central limit theorem tells you what is a stable distribution, which has the scale invariant behavior. In this work, Levy, if you see how he defines it, is Levy walks are mathematically useful for describing random batches of movement with the bizarre fractal properties that seem to have no place in biology. Fractal properties. What does fractal properties means? It means it has a scale invariant behavior, and that is why these distributions are much more interesting. In the sense, if you reduce this, if you scale down the x with a value, even then you'll have this kind of a same kind of a Gaussian distribution, and this can be seen probably in this number of different steps, like taken by a random walker with a plus or minus 1 probability, and this is what Feynman describes. The scale invariant of behavior can perhaps be seen here. Like you increase the number of steps also, but the distribution is still a Gaussian, but with a much more wider fluctuation. But the mean is still the 0 because it begins at 0. This random walker or whatever. But this is true for any stable kind of stable distributions, and this is what led me to study this kind of spread of a virus or something during 2020 when there was this corona break, and that was the point of the work. Like this distribution, if you take it as a country, or if you take it as a state, or if you take it as a whole continent as such, the distribution should have the same kind of characteristics, and perhaps that can lead to some kind of behavior on a large scale of how you can predict the spread is going to happen. And that was the motivation of those simulations, and yeah, that is the whole crux of this work as such. Yeah, okay, I have still time, and yeah, so far any
how would
queries?
you claim that the spread of virus is a stable distribution?
Yeah, for that, it is not really nice as such. Like, how would I claim that? But so this is all approximations, approximate analysis. My claim was that there seems to be a first wave and a second wave, which globally, if you see, or if you see in a state within a country, or you see in different countries, the behavior is kind of same. Able to understand what I'm saying? There is a initial peak and reducing, and again there's a peak and reducing, and these timelines can match if you scale them again. Is whole my point. Am I making sense?
Yeah. Mm-hmm.
Yeah. So yeah, this is not very exact or proper. This is just empirical, and this is very yeah. But that was the motivation for doing the simulations, and I was and the point of the simulation was to match which will have a better spread, the Gaussian distribution or the Levy, I mean the random walk or the Levy walk, which walk will make the spread faster, and that was the point of doing this distribution. And finally, it came out that Levy walks are better for the spread of a virus or something based on this simplistic simulations. There are many drawbacks with these simulations. The major problems I thought were the boundary conditions in the simulations, which are not nice. This is much more important, like finite size scaling effects. Like I take a finite boundaries here, if you observe, and these boundaries are not neat. I should make these boundaries like when this carrier or someone reaches the boundaries, the conditions are not so clear. So yeah, I cannot take an infinite boundary size. These are finite size simulations. But yeah, these are some of the drawbacks, and there is much more loopholes happening. Yeah, but this is a simplistic view of how you can study this kind of spread, perhaps. Yeah, and yes, that is the point. And is there any other query?
Yeah, I have a question. So before we do an analysis,
Yeah.
is it possible to, just based on data, is it possible to decide, is there some guide one can have that, oh, this distribution is better for this, or the another Poisson distribution is better, or normal or Lorentzian? What would you look
Yeah.
for? What are the factors you will look for to decide on that?
Yeah, this is very good. I mean, this is a research
Sure.
oriented question. Yeah, this, as I said, all we can do is take different distributions and match it with the data. That is what, even if you take these Nature letter papers, which they did, they just take the different data and they try to match it with the distribution. And if it matches nicely, I mean, closely, very closely, again, how closely you should ask. That's all we can try to predict it. That's all. And yeah, this all depends again on how much, what is it, I mean, limits you take. Like for instance, in the mobile phone users scenario, the paper seemed to have faced an issue when it was like low economic region. They segregated into higher economic region and low economic region, and there they could not match the data completely. They could only match this data with a higher economic region. And so there are many parameters which seem to play a role, but all we can say is just try to fit it with any distribution, whatever is available. And the stable distributions are nice, have a nicer behavior because of the scale invariant behavior. And that's all you can say, I suppose. Yeah.
Or maybe I can put it the opposite way. Let's take a very classic example where normal distribution is, we know that normal distribution is very applicable. And then we take another distribution, let's say the Lorentzian or a Lorentzian distribution, and try to fit it in. How much will be it off? Like what will be the error it will show? Will it be significant or will it be negligible?
Yeah, it will be, of course, it will be significant. And Gaussian does not work in all these cases. That's why I said Levy. Levy only works. Gaussian does not work in all this.
No, that is for, you took very not classic examples, like we didn't know what exactly it was. For example, I think, would it be correct to say that ideal gas
yeah. So
obeys, let's say, Gaussian, would that be right?
Yeah, the Maxwell-Boltzmann distribution
Correct.
is kind of Gaussian.
So now suppose I try to fit it with Lorentzian. How much off will I be? Will I get the 2 significant digits accuracy, or will I be off even in the first sig digit?
Again, you have to take for the Lorentzian all these cumulants, and you have to see that what are the cumulants in this Lorentzian. I would say that is the way to approach it. We definitely say it's a Maxwell-Boltzmann distribution because it has only 2 features, only 2 cumulants present, mean and variance, and remaining all go to 0. And that is one other important role from the central limit theorem. Remain all the cumulants go to 0. I don't know how the Lorentzian distribution is, but you need to take what are the cumulants of this Lorentzian distribution, and you try to see that. That would be more.
Yeah, got it.
Yeah. Correct way of approaching it, I suppose. Yeah, that's why I talked about the cumulants and how they are related to the movements. And in the same context of different distributions, stable distributions, again, now I'm going to go beyond it. And yeah, so this, for our simulations, we use this kind of steering behavior for autonomous characters. And I should also appreciate my co-author, co-author Sindhudha Rajadurai, who was very much helpful in doing the code for all these simulations. Yeah, and I should not go through this. Yeah, and one other interesting distribution, like which has this kind of long-tailed nature, and is the GIF distribution, which can be found in any language. If you take a big enough book, English book, not textbook, English book, and you try to distribute the words, how this they exactly seem to have a mathematical power law kind of behavior, which is this GIF kind of distribution, like which goes like this: D is present these many times, off is present these many times, and is present this many times, 2 is present this many times. And this is another long tail distribution which is found in textbooks. I mean, not textbooks, again, books. And this seems to be followed kind of, again, see, this is very bad approximation, one should say, like in different languages. This was well studied in kind of English books, and it was found to have this kind of GIF distribution. And this is again a review paper which seems to show this distribution. And these are some important stable, these are a family of distributions actually: GIF distribution, or Pareto distribution, or the Levy distribution, or a Gaussian distribution, family of the stable distributions. And I've just talked about the more interesting prevalent family, I mean parts of this family in the family of these distributions. And that's all I suppose. Yeah, thank you. Yeah.
Thank you, Venkat.
Thank you. Yes, hope I was
Open this for questions. I'm sure.
Yeah, hope it was a coherent.
Yeah.
So COVID is the only thing that you studied, or did you try something else?
No, the motivation came. No, I didn't even study COVID. I should not say I studied COVID. It's a very bad. That's why the work is called Levy simulations. That's all. The motivation was perhaps COVID can be studied through this. I did not do anything related to COVID. I just studied Levy walks and random walks, simulating them. I cannot study COVID. Those, if you ask me, can I produce those kind of curves, whatever happened in the different countries? I cannot. Yeah. I mean, I do not know how to produce this kind of, exactly match it with those kind of curves. Yeah. Again, the motivation is the models which are present already, which I'll not talk much about, which I also don't know much about. SIR models, and they do not capture the entire picture. Like there's this first wave, second wave, third wave kind of thing happening, and this cannot be captured with any other, I mean, models as such. Yeah, I should not say my this model works, but I could see this kind of statistical disturbance, like increase and a decrease, and again an increase and a decrease. These are like this is purely from the simulations, how the this blue dots are turning to red dots. But yeah, whether this I mean, what is happening with COVID, I cannot say. I should not say.
How reliable are these predictions with the words that you showed? If in the spirit that you said COVID is very hard to do an analysis of, how reliable are these predictions of the word distributions that you showed? I mean, I understand the distribution, they look visually very Poisson-like.
Yeah, that was my thought too.
But is it,
sorry,
is it reliable?
Sorry.
Can you make any predictions with that?
You mean the GIF distribution and
I mean, that's a distribution you gave, but my point is, how reliable are these? For example, with Gaussian distributions in a let's say in ideal gas law, we go forward and do a lot of predictions based on that, and things work. But can we do anything with that here, or how reliable are they? Or my question is very general, like in biology, I see a lot of statistical analysis, and often I don't have too much faith there. So is it wrong to say that, or is it okay?
Yeah, this, I would say you take a big enough book, and I would say the GIF distribution will follow. You take a large enough book with large enough pages and large number of words, the GIF distribution will kind of follow. Yeah. Okay. Yes. There's a lot of work going behind that. Yeah. And even Mandelbrot seems to be associated with it at some point in time. Yeah. And
Yeah, it's remarkable. Yeah.
Yeah. I mean, yeah. Ideal gas, as the name suggests, it's ideal. We cannot, it's, yeah, that cannot be compared with all this, whatever other studies, I suppose. Yeah.
It's because of 10 raised to 23, probably.
Yeah, yeah, as you said, 10 raised to 23. Yeah, yeah. I think in the case of gas, it's 10 raised to 18, I suppose.
Yes, yes.
Yeah, yeah. Anyway.
Any other questions? Yeah, John?
Yeah, so, yeah, great talk, Venkat. And,
Oh, thank you, thank you.
I'm not sure, if you mentioned this or not, but, so I guess what additional analysis can be done for stability versus, or unstable versus non-stable probability distributions, and if they have, yeah, any, maybe they indicate something physical, or if there's some physical property associated.
Oh, yeah. Stable distribution. Yeah, I don't know what is a non-stable distribution. Stable distribution is what what I meant by having, they have the scale invariant behavior. Like
Yes,
if so if you take the gas in this room, even if you take half the gas in this room, it will still have this Maxwell-Boltzmann kind of distribution, because 10 power 18 by 2 is not a significant decrease, I suppose. Yeah, but yeah, so the scale invariant behavior is very important thing which is used in the field theories as well, like the renormalization. I mean, I should not talk about renormalization in the quantum field theories, but I talk about in statistical field theories. The renormalization used in the statistical field theories depends on this kind of scale invariant behavior. That is where you can say that the degrees of freedom, or whatever I say, half the room, what I'm taking is half the degrees of freedom I'm taking away from the room. The degrees of freedom which have a correlations can be removed. And whatever left will be the uncorrelated degrees of freedom. And that is what you need to study. That's all. And yeah, I think I went too much. But yeah, that is one interesting thing you can take from the stable distributions, I suppose. Yeah. Did I make sense?
yeah, so, yeah, so pretty much just the same, in all physical context.
I don't. Yeah, in a physical context. I don't know what is non-stable distributions, but yeah, stable distributions have the scale invariant behavior, which is an interesting property by itself. Yeah.
Okay, thanks, thank you.
Yeah. Thank you. Thank you. Thank you.
Any more questions?
Venkat, can you hear me?
Oh, yes.
Yeah.
Yes.
Hello, sir.
Can you hear me?
Yes, sir. Yes,
Venkat,
sir. Yes, sir.
Go ahead.
Yeah. It's a nice talk.
thank you.
Yeah, congrats first of all. I just have a few points to clarify.
Yes.
Whether the Gaussian distribution is a special case of Levy distribution, can I say that?
Special. No. It's a special case of stable distribution. Yes, sir. Levy distribution is one of the stable distribution, and yeah. No. It's not a. I don't think Gaussian distribution is special case. Both
No,
have,
Levy. If I
yes, sir.
understand correctly, Levy actually found out a class of distribution which are scale invariant, right?
Yes, sir. Yes, sir.
Of which I suppose the Gaussian distribution is a special case. I'm not sure, but I have to check it.
You can get one from the other, because this is the probability distribution of a Levy, and this is for a Gaussian distribution. And yes, this has its own features, and this has its own features. Oh yeah, in fact, variance in kind of Levy distribution. Yes, sir. But here variance is finite. The what deviation is finite here.
Oh, okay.
Yes. I mean, if you also see this, keeps on going. Yeah, it doesn't die off. but Gaussian distributions die off.
Hello, can you hear me?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay. Actually, sometime back when I looked at this, the distribution of, chaotic systems in the phase space, usually what happens is that if the phase space is completely chaotic, they typically follow the Gaussian distribution. Okay. It's something like you're dropping an ink in the bowl of water, something like that.
Yeah, Brownian walk. Yes.
Yeah, Brownian walk kind of thing. That's what happened in the typically.
Yes.
That's how the trajectories are distributed in the phase space. If it is completely chaotic, if suppose suppose the phase space is not completely chaotic, if the phase space is a mixed phase space, that means majority of the regions are chaotic and some regions are you have some regular structures. In such cases, we observed that these trajectories they obey a Levy kind of distribution. That's what we observed. In our earlier simulations. So, which is common in very many mixed systems, not completely chaotic, but mixed phase spaces that we observed long back. Yeah.
Yes.
So the point is, these tiny regular structures in the phase space, they will be deviating the distribution away from the normal kind of.
Yeah.
A comment here, if the physical system itself is different, right? One is diffusion and the other is a normal distribution, correct? Isn't that physically different? The differential equation governing them is different? Like one is diffusion equation and the other is, what's the word?
I think super diffusive or something. Yeah, I think, there is
Something like that.
Yeah.
For example,
if you
look at a completely chaotic phase space and see how the trajectories are distributed in the entire available phase space region, they are normal. Normal, that is similar to how the how you have the ink is distributing over a bowl of water. That's a normal distribution. But that is not the case always. If you have a nonlinear system where the associated phase space may have some tiny regular structures here and there, those tiny regular structures disturb the distribution of trajectories in the phase space. It will be quite away from the Gaussian kind of.
Yeah. As you said, I think non-linearity seems to play a major role there. Yes.
Yeah, exactly. Yeah, very many nonlinear systems they obey the Levy distribution. Yeah.
Yeah, non-linearity will drive this.
And
Vipin.
And generally, these are actually called the anomalous diffusion.
Anomalous. Yeah.
Anomalous diffusion, and they're actually driven by fractional Fokker-Planck equations. Usually, the probability is actually driven by the fractional Fokker-Planck equations, whereas the Gaussian probability is actually driven by the usual Fokker-Planck equation. Yeah.
Correct.
Very nice. Yeah.
And again, adding to these Levy distributions, you have something called a stability index, which is alpha. So the alpha usually varies from 0 to 2. And if it's exactly 2, you call it the usual Gaussian distribution. And the alpha is 1, you call it the Gaussian Cauchy noise, stuff like that. Yeah.
It's useful.
So it's a general class of distributions where, defined by its characteristic function.
So can we say in that sense they all belong to one class? Gaussian is a special case of Levy?
Yes, definitely yes, because the characteristic function that you write for Levy noise reduces to that for Gaussian if you substitute alpha equal to 2. And of course, the skewness parameter also, if that you put it to 0, then that reduces to your Gaussian characteristic function.
Oops. That's
Can, yeah, can I just be reminded because like in quantum mechanics, you have the simple harmonic oscillator, but then only one state is Gaussian, correct? Only the ground state is Gaussian and the other states are non-Gaussian.
I didn't understand. How is
I
the
think
ground
the
state
question is, he's asking, John is asking, the probability of finding a particle in the ground state of, in the quantum mechanical ground state of hydrogen atom, sorry, not hydrogen,
What?
harmonic
Yeah,
oscillator
okay.
is the Gaussian. And if you are in the next state, it is given by Hermite polynomials, like they are derivatives of, or at least the Hermite functions. So,
Yeah.
so
Ooh. And yeah, so I didn't understand. Yeah.
so his, I think John's point
Yeah.
is that only the ground state is
Yeah. And
is
you have
Gaussian.
the
Okay, okay, okay.
Is
same
commenting, I
differential
think.
equation, yeah, yeah. Well, I guess
That is.
the E changes, but the eigen value changes, but
Is that also the same this probability distribution? Can we call it probability? But what is the probability?
yeah, so the ground state of the harmonic oscillator has a probability distribution.
Yeah, I understand. What is along x-axis?
That is the X, the
That's
position
X
of
position, yeah.
but I think that is the expectation value of a physical variable. Probability distribution is something that is applicable for a general setup.
I think it's the wave function though. The wave function isn't an expectation value.
Wave.
Oh yeah, that's correct. Yeah, it's a wave function. Yes, it's a distribution, probability distribution. Yes.
But yeah, I don't think we can compare that wave function with this probability distribution.
I think yes, right?
Like,
You know,
yeah,
why not?
Isn't that psi square x?
Yeah, psi
no,
square
we
x.
should
Yeah,
be
exactly.
able to compare
Psi
it.
star x, psi x?
Yeah, that is a probability distribution, right?
Exactly.
Oh, yeah. Wait. Okay. Oh, yeah. Okay. Psi star x, psi x.
That's a whole class of distributions there. Yes.
Yeah.
Yeah, good points. Yeah. I think.
yeah. I just, because we were talking about how probability distributions are associated with differential equations.
Yes.
Yeah, so.
Yeah, good points. Yeah. Any more comments?
Now I was just going to thank.
Yeah,
Okay. Thank you, Venkat. I'll stop the recording at this point, but we can keep chatting.
okay,
Yeah,
then I
thank you.
could
Thank you.
turn on my
everyone.
camera once the recording.